Okay, in this video, we're going to talk about functional equations. So functional equations are essentially an equation involving a function or sometimes multiple functions, and the objective is to find all of the possible functions satisfying that equation. A very common one, a very well-known one is Cauchy's functional equation. So it's a function from R to R that is preserves addition. In other words, f of x plus y is equal to f of x plus f of y. And it is not very difficult to see that for every positive integer n, f of n equals n f of 1. And that would be done by induction. And then you could show f of negative n equals negative f of n. And eventually you can put those together and find out that for every rational number r, f of r equals r f of 1. So that's something that you can do by induction. And if you have one condition on f, it could be monotone, it is continuous. In fact, just continuous at 0 is enough. Then you can show that in fact it's a linear function. So it must be c times x. So that's a really useful functional equation. Now, I want to go through a bunch of techniques that we use for functional equations, and then I'll show you in one example how to solve a specific functional equation. So first thing you want to do is you want to keep all of your work organized, because there's going to be a bunch of things that you're going to be writing, and some of it is going to be useful, some of it is going to be not very useful. And I want to keep your work really clean so that you can come back to those and see what exactly you have proved and how exactly you have proved. It happens very frequently that when I solve a functional equation, I end up with something and I think, oh, I proved it, but then I realize, no, I made a mistake along the way. So if I have my work organized, I'm able to go back and check my work. So start with evaluating functional equations at different values. Can you evaluate f of 0? Can you evaluate f of 1, f of negative 1, perhaps f of positive integers, perhaps f of integers, perhaps f of rationals? Depending on the situation, you might be able to evaluate some or perhaps all of them. In some instances, finding f of 2 may be as difficult as solving the problem. So keep that in mind. After you find a few values of f, then guess what f must be. And in some cases, there might be multiple possibilities for f. So find some functions that satisfy the functional equation. So some of the common ones are constant functions, linear functions, exponentials, perhaps x to the power of n, perhaps quadratics, perhaps cubic, perhaps all polynomials. Things like that may help you understand like what are the solutions to the functional equation. Because if you don't know what you're trying to prove, then you won't be able to prove it. So keep that in mind. Then try to see if you can find some properties of f. Is it odd? Is it even? Is it decreasing? Is it one-to-one? Is it onto? Are there any cyclic functions involved? So cyclic functions means functions of the form, so we call a function cyclic function if when you apply it twice you get x, or if you apply it 3 times you get x, etc. So if you have any of these sort of things, you say phi is cyclic. So can you prove that the functional equation satisfies the functional equation? And in every step, you want to go back and see whether the results that you obtain is going to simplify your functional equation. If you're stuck, if you're not able to solve the problem, it could be the case that you're trying to prove something that is false. So if you're trying to prove that the functions are only linear functions and you're stuck, it could potentially be that maybe that's not the answer to the question. So just keep that at the back of your mind, because that also happens fairly frequently. So I want to take the time to solve a problem from IMC. So this is problem number 4 from 2018 IMC, International Math Competition. It is clearly a functional equation, so we're trying to solve for f. We're trying to find all functions, differentiable functions that satisfy a certain functional equation, a certain relation between f and, in this case, f and f prime. So you could start with plugging different values for a and b. So one obvious thing to test is, let's plug in, say, a equals b. If you plug in a equals b, what you end up getting is 0 on one side and 0 on the other side. So this is really not useful. Then you could start plugging different values. So unfortunately, I cannot plug in anything negative or 0. So maybe you'll start from plugging some value for a or plugging some value for b, and then figuring out what we get. So let's say you want to plug in, let's say you want to fix one of the variables. Let's say you fix a, and you plug in some value for b. So let's say f of x minus f of a equals x minus a, f prime of root ax. So something like that seems plausible. So now if I look at this one, that kind of reminds me of mean value theorem. So this is my scratch work. This is not a solution yet. I don't know what the solution is going to look like at this point. So I write it down like that, and that reminds me of mean value theorem. But again, at this point, it's not quite clear how that would be relevant. The fact that this looks like mean value theorem may not be of much help. So when I look at this, I see that, okay, I can try to maybe make ax a constant and then see what I get. So if I plug in, say, 1 over x for a, I get f of x minus f of 1 over x equals x minus 1 over x times f prime of 1. So that is interesting. That's kind of like saying you have f of x minus f of 1 over x, that's equal to f prime of 1x minus f prime of 1 over x. So maybe, and we don't know yet, maybe if we take something that these two are equal and these two are equal, that is going to work. So from here, I guess that f of x equals perhaps cx plus d, or I would have to pose a question here. So does this work? Now, the answer may be yes, the answer may be no. We don't know yet. This is easy to check though. You could take that, plug it back into the equation. So it is c, so the equation was f of b minus f of a. So that is cb plus d minus ca plus d. That is just simply c times b minus a. And on the other side, we had b minus a times f prime of root ab. Well, f prime is just a constant c, so that gives you b minus a times c. Okay, so that's a check. So every linear function does work. But the big question here is, are these the only solutions? So are linear functions the only possible solutions? Well, it's not quite clear whether they are or not, but what I did at this point was I took f of x equals cx squared plus dx plus e, and then I substituted that into the differential equation, that I'm given. I'm not going to go through the process of that. And then I ended up, well, I can't actually figure out any quadratic. It doesn't look like quadratics work. So maybe the answer is all of the linear functions. So since I have derivative here, I would have to show that it is linear. So in other words, I have to show that its derivative is a constant. So perhaps linear functions are the only solutions. So what we need to show f double prime of x is equal to 0. So that's what I need to show. But I don't even know if the function f is differentiable. All I know is this. I know f of b minus f of a equals b minus a f prime of root ab. That's what I know. I don't know whether f has a second derivative. But what I do know is that f prime is in terms of f. So this is differentiable because f is differentiable. Therefore, I'll have to kind of justify that further. Therefore, f double prime does exist. Then I wrote it down in this form: root ax equals f of x minus f of a over x minus a, so that I can differentiate. And I differentiated that, and then I couldn't see how I can prove that f prime of f double prime is equal to 0. At this point, I was not successful in proving that f double prime is 0. So what I thought is, I remembered that, well, I may be wrong that these are the only solutions. Then I tried. F of x equals x to some power, x to the power of n. I took that and plugged it into the differential equation that they gave us, into the functional equation. And to my surprise, I was able to find another solution. So substituting this, we are able to get f of x equals 1 over x as another solution. Okay. Then I thought, well, maybe these are the only solutions. But then I realized that if I take two solutions, if you look at the differential equation, if you look at the functional equation, if you have two solutions, let's say g is also a solution to the same thing. When you add them, you get another solution. So then f plus g is also a solution. Okay, so that's nice, but, well, I'm still not quite clear on how to solve the problem. So what I showed is, we showed so far that f of x equals a plus bx plus c over x is a solution. Okay, so now it could be that I have more than this. There might be multiple solutions. Maybe this is not the only solution. Maybe there are other solutions. But at this point, I haven't been able to find anything else. So let's at least attempt and see if I can prove this one. So going back to what we did, we showed that f of x minus f of 1 over x is equal to x minus 1 over x times f prime of 1. Okay, so this is what we have now. Now the question is, can I find f from here? So looking at this, I realized that, well, it doesn't look like we are in a very good position to actually solve this problem using only this equation. So we seem to need more information to be able to solve the problem. So I'm going to go back to the original equation, which was f of b minus f of a equals b minus a f prime of root ab. Initially, I had taken the second derivative from this equation, f of x minus f of a equals x minus a f prime of root ax. So I'm going to take the second derivative because at that point, I wanted to find the second derivative. I wanted to show that the second derivative is 0. So let's take the second derivative of f, which on this right side, it would give you a second derivative. So it would be x minus a f double prime of root ax times, that's it, there's a 1/2 root a x to the power of negative 1/2, and then plus f prime of root ax. So I have that. Then looking at this is interesting because I see ax on both of them. So I can now plug in some value for a in order to make that a constant. So then I thought about substituting a by 1 over x. So that gives us f double prime of 1 plus root a over root x, and there's a 2 at the bottom, plus f prime of 1. Then I realized, well, I already have, I'm sorry, this is multiplication. Yeah, so so basically now I can take the integral of the right hand side and obtain what I am looking for. So that shouldn't be a problem at this point. Okay, so we'll just do that. So we have f prime of x is equal to, so if you multiply that out, that would be just some constant times root x. Okay, let me see. I feel like there's something not quite right about this. Oh yeah, so I didn't replace the 1a here by 1 over x. So that becomes that. And the next thing I'm going to do is I'm going to just integrate that. So you'll just integrate this and then you're done. Okay, so now I'm going to write down the solution. So I'll tell you what how the solution is going to look like, and then we'll go, we'll just write it down. So here's the way you want to write down your solution. So the first thing you need to show is that you need to write down is your answer. So the only functions that satisfy this functional equation are f of x equals a plus bx plus c over x for constants a, b, c. Okay, so first we'll show ax plus or a plus bx plus c over x is a solution. Okay, so I won't go over the details of how that can be done, but you simply take that, plug it into the differential, into the functional equation that they gave us, which in this case is also kind of a differential equation, and then you just show that they are equal. That's the first step. Next, substitute b equals x and differentiate. So we have f of x minus f of a equals x minus a f prime of root ax. We get f prime of x equals f prime of root ax plus x minus a f double prime of root ax times 1/2 root a x to the power of negative 1/2. Substitute a equals x, A equals 1 over x, and we get f prime of x equals f prime of 1 plus x minus 1 over x, f double prime of 1 times 1 over 2x, which is f prime of 1 plus f double prime of 1 over 2 minus f double prime of 1 over 2x squared. Now integrate to obtain, so we get f of x. So if we integrate, we're going to get f of x. Then we get f prime of 1 plus f double prime of 1 over 2 times x plus f double prime of 1 over 2x plus a constant. And that completes your solution. So you just want to make sure that you write down your final answer at the beginning. So it's very important to write down this at the very beginning. Make it clear that you know what you're doing, and then write down the rest of it. And you have to show two things. First, these are solutions. First, the ones that you're claiming are solutions are solutions. And second, why these are the only solutions. Okay, so I'm going to end that here.